And let me try to give you a hint on why by providing an application of this type of considerations in a field totally different from physics or mathematics. Let's look at biology. And let's think about a forest and two species living in the forest. Wolves and hares. And of course, there is some interaction between them, right? So, some wolves eat some hares. And what we would like to know at this point is what happens to those species in time. So, for example, we can go into the forest and count, at least approximately, how many wolves we have now and how many hares we have now. Is there any way for us to predict what will be the population of these species in the future? So, in other words, making this question mathematical, if we think about the population of wolves and denote it by a variable w, we can think of that as a variable depending on time, and the population of hares is another variable depending on time. And then we might want to see a relation between those populations, and a model that we may want to consider is the following. We may look at the rate of change of the population of wolves and relate it to the population of wolves and hares. And the first simple model would be to say that the rate of change of the population of wolves is proportional to the population of wolves itself. And why is that? Well, because the greater the population we have, the faster it grows, and the coefficient with that, let's say 0.3 to be specific, would be the birth rate of wolves. Now, how does the rate of change of the population of wolves depend on the population of hares? Well, of course, hares provide food for wolves. So the more food we have, the faster we grow. So that means that we probably have that rate of change proportional to the population of hares with some coefficient. And that coefficient is positive in the sense that the more food we have, the faster the population of wolves grows. So this is the coefficient responsible for the dependence on food. Now, what about hares? The rate of change of the population of hares, is it proportional to the population of wolves? Well, probably, because the more wolves we have in the forest, the more dangerous it is to live in the forest. And the coefficient here is negative, and it basically measures how many hares would an average wolf eat in time. But the population of hares also depends on the rate of change depends on the population itself, and the coefficient is going to be the birth rate of hares, and that is much greater than the birth rate of wolves. And that's exactly what is supposed to compensate this negative rate from predators. So this, let's put it, 5 times h. So this is dependence on predators this is the birth rate. Of hares. And that was the birth rate of wolves. Alright, now having this model for the change of the populations, what is the relevance of this model to our consideration of linear functions from a plane to a plane? Well, the relevance is that we can now put those two variables together. So let me put them together, and together W and H would make a point in the plane with coordinates W and H. So we may think about this coordinate plane, and we may think about the current state being a point in that plane when we count the number of wolves living now and the number of hares living now. And what we want is to trace the path of this point in the future, because the population of wolves and hares will change simultaneously and this point will move in the plane. And then by tracing that point, we would see what happens to the populations. For example, if that point moves here, that means population of hares vanishes at some time in the future, while the population of wolves doesn't. So that's the kind of consequences we would like to make, the kind of predictions we would like to see. So we interpret this pair as a point in a plane, so we got a plane. But then the derivative of that is going to be the pair W prime H prime, and that can be thought of as the velocity vector of that point, the rate of change of the position in the plane. And now we might think about assigning the vector, velocity vector, to every point on a plane. Because for every single point on a plane, these equations of our model describe the velocity vector at that point. So our model actually defines a vector field in that plane. So we have just interpreted our model as a vector field, and our vector field happens to be linear, and it is described by this matrix: 0.3, 0.2, negative 0.7, and 5. So those four coefficients put together provide us a matrix, and this is the matrix M we can think about. And what we know so far about 2x2 matrices and about linear vector fields is that this matrix can be decomposed as a sum of three: gas-like matrix, liquid-like matrix, and solid-like matrix. And then those are significantly simpler, represent simpler behaviors, and can be studied independently. And an interesting question would be now, what if our matrix M is purely gas-like matrix? What kind of consequences can we make about this biological model? Well, let me look at those cases here. So if we have gas-like behavior, and I keep this terminology from physics, although I'm talking about biology. Well, the reason is that I don't know if there is the corresponding terminology in biology. So I will just use physics terms that we used to apply, And gas means that what we will see in this plane with population W and H, it will be either expansion from the origin or shrinking, and that depends only on one number, on that coefficient lambda. And if it is expansion, that means no matter where our original point is, our current state, the population of wolves and hares will increase, and those populations will stay proportional to each other. They will keep the same proportional as now. So if you want to preserve, if you don't want anybody to die, any of these species, you just leave them alone. They will survive. Now, if instead of expansion we have shrinking, that means no matter what the current situation is, in the future both populations will decrease, and they will decrease to 0. So in this scenario, in case of shrinking gas-like, well, we definitely have to do something if we don't want those species to die out. Now, what about liquid? What kind of scenario we may see in that case? Well, in that case, on this WH coordinate plane, we expect to see two perpendicular lines. Let's say this one and that one. And the flow is basically along these lines. So if the flow along this line is away from origin, then the conclusion is wherever you start, the evolution in the future will result in the populations growing, and the proportion between these populations is going to approach the slope of that line. On the other hand, if the behavior along that line and along this one, the line in the first quadrant, is the opposite, if everything is shrinking along that line, that means again that no matter where you start, we will end up on the coordinate axis. But the results now are going to be different. Right? If we start below this line, we will end up with the population of hares dying out eventually. If we start above that line, the population of wolves will die out and hares will survive. And, well, finally, with the circulation behavior, if our matrix represents purely circulation, we will see either behavior that brings us to the population of hares dying, or to the population of wolves dying out. So this is the sort of analysis we can do at this point about the biological system. And all of that is brought to you by this simple decomposition into gas, liquid, and solid. It resulted from our basic understanding of any flow in terms of three very basic flows.